So we will continue with optimal binary search trees. So we have derived our recurrence relation. I will rewrite it. E ij. So Eij stores the optimal cost of the binary search tree. So this is equal to Qi minus 1 if j is I minus 1. This is the smallest subproblem. Otherwise we have Eij is equal to minimum overall R ranging from I to j. Left subtree, it has cost Ei R minus 1. Right subtree, it has cost E R plus 1j plus weight of the complete subtree I to j. This if I is at most j. And we also have this the equation for weight. We'll further simplify it for our calculations. So our Wij is Wi R minus 1 plus PR plus W R plus 1j. So we'll further simplify this equation. So here we notice that we can take any value of R for this computation of Wij. So for our convenience, we'll take the special value R equal to j in our algorithm. So in this equation, what we do is simply put R equal to j. So here just set set R equal to j and simplify the expression. So we get simplified form of Wij that we will use in our algorithms. Wij is equal to just putting the values, we get Wij minus 1 plus Pj plus W j plus 1j. Now what is Wj plus 1j? It is simply Qj. So again this further simplifies to Wij j minus 1 plus Pj plus Qj. So this we'll use in our algorithm for computing Wij. So Wij depends upon smaller subproblem Wij minus 1 plus the constant Pj plus Qj, and Eij again it depends on smaller subproblems Eir minus 1 and Er plus 1j, and additional is Wij. So in addition to the tables, E for computing the optimal cost, W for computing total cost, you also maintain the optimal root in the table root. So this root Ij is R such that Kr is the root in the optimal binary search tree. With the keys Ki up to kj, and with dummy keys di minus 1 up to dj. So this also we maintain, so that at the end we can actually recover the optimal binary search tree. So we keep track of this minimum r and store the result in root ij. So now with this we write our algorithm. So we will analyze the algorithm as written in the textbook, Corman, Lizerson, Rivestein, Introduction to Algorithms, and we'll show that its time complexity is big theta of n cube and space complexity is big theta of n square. So we write the algorithm. So we call our algorithm Optimal BST. The vector P of probabilities of keys, Q of probabilities of the dummy keys, and N number of keys is given. So first we initialize the tables. E, the cost table, I index is from 1 up to n plus 1 and j index is from 0 up to n. Weight table is also identical, 1 up to I index ranges from 1 to n plus 1 and j index ranges from 0 to n. We also maintain root table. Root is from I index from 1 to n, j index also from 1 to n. So we create new tables. So first we start with the smallest subproblem. So we have a for loop I is equal to 1 to n plus 1. We compute the cost and the weight. So the cost is trivial cost for the dummy nodes I minus 1. This is the smallest subproblem. Initialize it with qi minus 1, and same way the weight is also same, I to I minus 1 is also qi minus 1. So after this, so this is the smallest subproblem. We can say that it is of size 0 because it has only a single leaf node, no non-leaf node. So next we proceed with the subtrees with non-leaf nodes. So starting from the smallest, having a single non-leaf node, going up to a maximum of n non-leaf nodes. So we have a for loop. Size parameter here is L. L is 1 to n, starting from problem of size n going up to n. So once the problem size is fixed, we fix the parameters I and j. So next level of for loop we have I can range from 1 up to a maximum of n minus L plus 1 because the problem size is L. Once I and L are fixed, j has a fixed value. J is I plus L minus 1. Next, for finding, so cost we have to minimize, so we initialize with a large value written as infinity. E ij eij, we initialize as infinity. Then wij we compute. So just using our earlier formula, wij is this wij minus 1 plus pj plus qj. Then we have another for loop for all possible values of r, where we have to minimize. So next we have a for loop, r is equal to r, so r can range from I to j. So we compute the recurrence formula and keep track of the minimum. So t, the temporary value, we compute e using the formula ir minus 1 plus e. So these values are already calculated because these are smaller subproblems. R plus 1j plus wij. So wij is already computed before. Now next we keep track of the minimum. If we are getting a new minimum, we save it. We save both cost as well as information of the root. So cost is saved in ij and root information in the root table. Root ij will store value of r. Finally, we return the cost table and the root table. Return e and root. So once the values are returned, our optimal cost is E1n, and we can easily reconstruct our binary tree using this root table. So what we have to do is, so this algorithm is the above algorithm is step 3. So this algorithm is step 3 of the dynamic programming algorithm, computing the expected search cost. Expected search cost of an optimal binary search tree. This is the algorithm of step 3. So here we have only computed the optimal cost using E1n. So the last step is actually building the tree. Again, it is very easy with these two information given. We can easily compute. So this is step 4, finding the actual solution, not just the value. In dynamic programming, step 4 is making the optimal binary search tree from the root table. So again, this is very easy. So what we do is, so the initial problem, we are given these keys k1 up to kn. So just we break this at root. Just consider the root table. What is the root for 1 to n values of the keys? So initially we start here, just make this root and again recursively apply the same algorithm. So this root 1n becomes the root of the original tree, and we recursively apply the same algorithm for left and right subtree. So left subtree, it goes from k1 up to k root 1n minus 1, and right subtree goes from, starts from k root 1n plus 1 goes up to kn. So here, just for simplicity, I have not shown the dummy keys. So dummy keys you can imagine with corresponding dummy keys d0 going up to dn. So here also d0 going up to d root 1n minus 1, and similarly here dummy key d root 1n going up to dn. So then once again just apply recursively using the same root table to the left and right subtree and keep doing this. So in linear time we can recover. So now we will find the time complexity of our algorithm. So we can easily see the dominating term is the 3 levels of for loop, 1, 2, 3. So if we consider the innermost for loop, this, so here line 11, 12, 13 and 14. So we are doing constant number of steps, we can easily see. So how many times this for loop goes from r equal to I to j. So here this total frequency of this for loop is j minus I plus 1. Now j minus I plus 1, it has a very simple expression. If we look here, so this implies j minus I plus 1 is L. So here we have simplified that innermost for loop runs for this much time. So its complexity in terms of big theta notation we can write as big theta of L. This is time complexity of the innermost for loop starting at line 10. Now next level of for loop is at line 6, and here again in addition to big theta of L, again it is performing constant number of steps. So this consumes this, we can also write it as big theta of L. Now what is frequency of for loop at line 6? So this is I equal to 1 to n minus L plus 1. So this is the frequency. So net complexity of this for loop of line 6 is, just take the product, big theta of n minus L plus 1 times L. This is the time complexity. Now for line 5, just add this for L equal to 1 to L. So the same thing we have to add for L equal to 1 to n. We get our time complexity. So we can write this as, call this T2n. T2n is sum of L is equal to 1 to n, and the products are L and n minus L plus 1. N minus L plus 1 times L is big theta. So now we can write this sum. Just take big theta out. Sum of L is 1 to n. Simplifying this, we get NL minus summation of L is 1 to n L square plus sum of L is equal to 1 to n. So again we simplify this as big theta of n, we can take out sum of L is equal to 1 to n L minus sigma of L is equal to 1 to n L square plus sigma of L is 1 to n L. So this we can make one term and write big theta of n plus 1 times. So just directly writing the formula, this is n plus 1 by 2 sum of n natural numbers minus sum of square of natural numbers n plus 1 to n plus 1 by 6. So we are getting cubic expression. Again we are not interested in finding exact time complexity, only in asymptotic notation. So here again the dominating part is n cube, big theta of, what is coefficient of n cube here? 1 by 2, n cube by 2 minus, here it is 2n cube by 3 means n cube by 3 plus other terms, lower terms. So we get the time complexity as big theta of n cube. Now for space complexity, you can easily see it is very simple. Big theta of n square. You can actually see the tables. We are using quadratic tables. So first table is n plus 1 cross n plus 1. Second also same. Third is n cross n. So in big theta notation, big theta of n square. So space complexity is big theta of n square and time complexity is big theta of n cube. Now the same example that we started, we'll apply this algorithm and construct both optimal cost as well as the optimal binary search tree with the same given values. So once again we write our P and Q values. So the values of P and Q's are P1 is 0.15, P2 is 0.10, P3 is 0.05, P4 is 0.10 and P5 is 0.20. Now Q values are Q0 is 0.05, Q1 is 0.10, Q2 is 0.05, Q3 is 0.05, Q4 is 0.05 and finally Q5 is 0.10. So first we make the weight table. Weight table is very easy to find, very simple. Then we will construct the cost table and at the same time the root table. So we start with the weight table W. Weight table. So here again we have I and j values. I ranges from 1 to n plus 1, that is 1 to 6. J will range from 0 to n, means 0 to 5. So we make it again in the same way. Having 6 rows and columns. Divide this in 6 parts like this. Here also same division. And make the table. And here left we have j values, right we have I values. So this j ranges from 0, 1, 2, 3, 4, 5. I ranges from 1, 2, 3, 4, 5, 6. So at the bottom we have the smallest subproblems, I with I minus 1. So this is 1, 0. This is 2, 0, 2, 1. This is 3, 2, 4, 3, 5, 4 and 6, 5. So these are smallest subproblems. So what values we store is the Q values, Q0, Q1, Q2, Q3, Q4, Q5 in the order. So the values are 0.05, 10, 05, 05, 05. So all values are 0, 5 except for 1 and 5. 1 and 5. So we write the values 0.05, 0.10, then last value is 10 and 0.05, 0.05, 0.05. So next, for computing the next level of values, so given any ij is computed in terms of ij minus 1, means just below it, like this, in this pattern. So we have to consult this value plus the corresponding pj plus qj values. So here it will be p1 plus q1 value. This way we have to add. So p1 plus q1 value we find and add it, and so on. So one by one we say p1 value is 0.15, q1 value is 0.10, sum is 0.25. So we have to add 0.25. Here we get 0.30. 0.30. Same way we continue. So for computing W12 value, add this to P2 plus Q2. P2 plus Q2, 0.10 plus 0.05 is 0.15. So add 0.15 here. We get the value 0.45. 0.45. Same way we continue. Here we add 3, P3 plus Q3 value. P3 plus Q3 value 0.05, 0.05, we get 0.10. So we get 0.55. Here P4 plus Q4 value we add. P4 is 0.10, Q4 is 0.05, net is 0.15. Add 0.15, we get 0.70. Now finally P5 plus Q5 value we add 0.10 and 20, 0.30. So 1 we get value 1.00. So exactly same way all computations we have to do. So here P2 plus Q2 value we add. P2 plus Q2 value 0.15 we add and get 0.25. Next here 3 values we add, 0.05 and again 0.5 we get 1, 0.1, 0.35 we get. Same way we continue. 4 values here we have to add, 1 0 and 0.5 we get 0.15. So we get here 0.50. And last value here 5 values. 5 means 20 and 1030. 30 means 0.8 we get 0.80. Next here 3 values. 3 values are 0.5 and 0.5 1 10, so 0.15. 0.15. Next 4 values. 4 are 10 and 0.5 15, 0.15. So 0.30 we get 0.30. Here 5 values. 5 means 10 and 20 30. 6 0.6 we get 0.60. Here 4 values. 4 values are 10 and 0.5 15. 15 means 20 we get 0.20. 0.20. Next 5 values. 5 values are 10 20 30. 0.5 we get 0.50. Now here again 5 values, 10 20 30, 0.35. So these are W values and they will be used in computation of E values. Now next similarly we make E tables, cost tables. Exactly same way we make like this. This time I will make big table to accommodate the values. Divide this in 6 equal parts. Like this. And complete it. Again similar index values. Left we have index j, right we have index I. J ranges from 0, 1, 2, 3, 4, 5. I ranges from 1 to 6. 1, 2, 3, 4, 5, 6. So again structure is same. The smallest subproblems we have the q values. So q value just copy as it is. So second value is 1 0, last value is 1 0, remaining are 0 5. Just write it 0 0.05, 0 0.10, 0 0.05, 0 0.05, 0 0.05, 0 0.10. So now next level of problem, how we compute. So we look at the smaller subproblem. So here this is 1 1. 1 1 means the root is 1 and we have the leaf. So here it is very simple. Just add these cost. So just remember the formula how we compute. So we have to add W11, we have to add W11 value, we have to add 0.30, we have to add to the sum of these values, the subproblem values. So these are the subproblem values and this is the split point. Here we do not have any choice. Split point is 1, root is 1, so we record this in root also. This plus W value here. W value here is 0.30. Add everything, we get 0.45. 0.45. We have to keep track of root also. So we make root table also. Slightly smaller root table. Having 5 divisions. Like this. 1, 2, 3, 4 and 5. And the indexes are same way, j and I. Slightly different, 1, 2, 3, 4 and 5 and 1, 2, 3, 4 and 5. So we keep track of the root. Here root there is no choice of root at this level. It will be the same. So lowest level I can write here itself 1, 2, 3, 4, 5. And same computation applies everywhere. Just take corresponding W values, add these values. So next we see 0.15 added with this 0.25. So net we get is 0.40. 0.40. Same way we continue. Here 0.05 plus 0.5 we get 0.10. This value 33 value. 33 value is 1.5. So we get 0.25. 0.25. Same way we continue here. 0.10 plus 44 value. 44 value is 20. 0.30 we get. Next 5.5 value we add 1.5, the sum. 5.5 value is 3.5. So we get 0.50. Now next level we have two possibilities. So this is 1 2. So 1 2 we can split either at 1 or at 2. So first possibility, this problem is 1 0. 1 0 means we are splitting at point 1, and the sub problems will be we are splitting at 1. So 1 0 plus 1 0 plus 2 2 2 2 2 this. So this and this. So again same pattern, these two or these two. So first we consider this. So again idea same, we have to consider the sum, add with this w value. So w value is common to all. So first we determine the minimum and then we add finally to save our computation. So this combination is when we split at point 1, so 0.45. Second option is 0.50. So this option is better, split at point 1. So we take this, save root as 1 here, 1 to root is 1. 1 to root is 1, and the sum is 0.45 plus this w value, 1 to w value. 1 to w value is 45, 0.45. 45 plus 45 is 90. 90 we write 0.90. Same way we continue here. Again the two possibilities are, this is 2 3. First option is we break at point 2, split at 2. So this combination gives 3 5, and this combination gives 4 5. So 3 5 is better. So it is splitting at point 2. So we keep track of this. And then we keep track of this, right? This has 2. This combination is 3 5, 3 5 plus 2 3 weight. 2 3 weight is again 3 5. So we get 70. We get 70. 0.70. Next we have is this 3 4 value. So we continue. So 3 4 value, again we have two possibilities. 3 to 4 split at point 3. So 0.005 plus 30. Second we get 3 5. 2 5 plus 0 5 we get 30. So this is better choice. So this is 3 3 means we are splitting at point 4. So 3 4 splits at 4. 3 4 3 4 splits at point 4. Just note it, 4, and then we perform the computation. 3 0 we have to add this weight, 3 4 weight. 3 0 fit, 3 4 weight. 3 4 weight, 3 0 3 0, we get 6 0. We get 6 0. 0.60. Here this is problem 4 5. Again we have two possibilities. 0 5 plus 5 0 we get 5 5. 3 0 plus 1 0 we get 4 0. So this is better possibility. So here this is 4 4 means it is splitting at 5. 4 5 is 5. 4 5 is 5. So we note this, and then 4 0 we add with this weight, 4 5 weight, add 4 0. 4 5 weight, add 4 0, we get 9. 0.09 0.90. 0.90. Same way we continue here. 1 3. So this time we will have three possibilities like this in the same pattern. 1 2 and 3. We have to choose the minimum. So first combination is gives 75, 0.75. Second combination gives this 0.70, 0.95. So this is better, 0.70. So we note this is splitting at the point. This is 1 1 means it is splitting at point 2. So 1 3 is 2. 1 3 is 2. 1 3 is 2. Right here 2. 0.70 we add with this weight. 1 3 weight. 1 3 weight. 1 3 weight is 5 5. 5 5 5 5 plus 7. So we get 1.25. 1.25. Same way we continue. Here again we have 3 possibilities like this, and here we get 70, again 70, 75. So we can choose any, either this or this. If we choose this, then it is splitting at point 2. 2 4 is splitting at point 2. 2 4 is splitting at point 2. So we note 2. 2 4 is splitting at 2, and sum we have to make is 7, 0.70 to this 2 4 weight. 2 4 weight. So 0.7 plus 0.5 we get 1.2. 1.20 we get 1.20. Now here again first combination gives 0.95, second gives 0.75, third gives 0.70. This is the minimum, and split point is, this is 3 4 means splitting at 5. So 3 5 value is 5. 3 5 value is 5, and we update the weights. So here we have to add 0.7 to 3 to 5 weight. 3 to 5 weight 7. So 1.3 we get the value 1.30. 1.30. So next is 1/4 subproblem. Here again we will have 4 combinations. We will see which is the minimum. First combination 0.05 plus 1.25 we get 1.25. Second gives 1.05. Third gives 1.2, 1.3. So this is the minimum, 1.05, splitting at point 2. Splitting at point 2. 1 4 is 2. 1 4 is 2. Splitting at point 2. 1.05 we have to add to 1 4 weight. 1 4 weight. We have to add 1.05. So we get 1.75. 1.75. Next we have 2 5 problem, subproblem. Again 4 possibilities. We'll look one by one. First combination is 1.40. Second is 1.30. Third is 1.20. And fourth is 1.30. So 1.20, this combination, splitting at 0.4. So note that it splits at 0.4, 25 value splits at 0.4, and the cost was this splits at 0.4. 1.20 we have to add 1.20 to weight 25. 25 weight is 0.80. So net we get is 2.00. 2.00. Now the final value, we have 5 combination, we see which one is the best. First combination 2.05, next 1.75, 1.8, again 1.75, 1.85. So there are two combinations of 1.75. We can take this one, splitting at 0.2, 1.75, splits at 0.2, splits at 0.2, 1.75, we have to add 158, so we get 2.75. So this is the optimal cost. And how we reconstruct our root? This is the root of our original problem, so we now reconstruct. So K2 is the root of the original binary search tree. So once we split at 0.2, at the left, so left we have this sequence K1, right we have this K3, K4, K5. So again, just for simplicity, I am not drawing the dummy nodes. These are along with this D0, this D0, D1, D1. Here it is D3, D4, D5. So here it is, the problem is trivial. 1 1 1 1 is already splitting at 0.1 from this table. So this becomes like this: K2, left we have K1 and with dummy leaves D0 and D1. Next we proceed with 3 5 values. So 3 5 we see 3 5 splits at 0.5, and this one splits at 0.1, splits at 0.5. So K5 is the root. Right will have dummy node D5, and at the left what remains is 3 4, K3, K4 along with the dummy nodes D2, D3, D4. So once again we look at 3 4 value. 3 4, it splits at 0.4. So again this becomes, we continue, K2, K1 is identical, K2, K1 and D0, D1. Left side, right side we have K5, D5, K5 and D5, and left side. So left side it is splitting at 0.4. So here we have K4. Here we have K4, and left what remains is K3. K3 along with D2 and D3. So this is easy to solve problem. Next we look 3 3. So 3 3, there is no option. It has to split at 0.3 with dummy nodes D2 and D3. So final tree becomes K2, K1, K2, K1, D0, D1. Then at the right is K5 along with D5, K5 along with D5. Now left to K5 is K4, K4. K4, I forgot to add D4. So K4 along with D4 at the intermediate step. So K4 along with D4 and at the left we will have K3 along with D2 and D3. K3 along with D2 and D3. So this is the complete binary search tree K2. So we can see the in order traversal, we get in sorted order D0, K1, D1, K2, then D2, K3, D3, K4, D4, K5, D5. So this is optimal binary search tree. Optimal binary search tree, and cost we have computed, already computed, is 2.75. This is the optimal cost.